Hi everyone. In this section, we will talk about bit manipulation techniques, and these are nothing but these are some, maybe you can say, algorithms using which you can modify the data at their binary representation level. And every programming language provides us some bitwise operators which allow us to operate on the binary representation of the data that we have. Okay, so we will look how to use these bitwise operators, what are the different types of bitwise operators, and how we can use them to solve some problems. Okay, and the reason why we use bitwise operators sometimes is because they operate on the binary representation of the data, and they are fast as compared to if you use the non-bitwise operators. And what are the different types of operators you can see on the screen, and we are going to talk about AND, OR, XOR, ones complement, binary left shift, and binary right shift. Okay, so these are the bitwise operators, and if you're new to them, so let us explore each of them one by one. So the first one is a binary AND. So basically, let's say AND has very simple rules. Let's say you have two bits, one, and let's say the other bit is 0. So if you do AND with a 0, then it is going to give you a result of 0. Similarly, 0 and 1 is going to give you a result of 0, and only when both the bits are set, only then you will get a result of 1, and 0 and 0 is also going to be 0. So anything done an AND with 0 is going to give you a 0 bit. Okay, so these are the simple rules of doing a simple AND. And now how do we use it? Okay, let's say I have a number 5 and I do a AND with 7, then what I'm going to get? So let's see. So 5 in binary is represented as 000 followed by, let's say, 101, and it's a, let's say, 32 or a 64 bit number. 7 in binary can be represented as lots of zeros followed by 111. Now if you do AND, so it will happen on bit by bit level. Okay, so 1 and 1 is 1, 0 and 1 is 0, 1 and 1 is 1, and followed by lots of zeros. Okay, so if you convert this number back into the decimal, you will see this result is going to be 5. So this is how binary AND works. So I hope this is clear. And now let's see what is binary OR. So the rules of the OR are very simple. If one of the bits is 1, then the result is going to be 1. For example, 1 or 0 is going to give you, okay, so this is denoted using this operator. So 1 or 0 is going to give you 1. Similarly, 0 or 1 is going to give you 1. 0 or 0 is going to give you 0, and 1 or 1 is going to give you 1. So if one of the bits is 1, then the resulting bit would be 1. For example, if I do 5 or with 8, okay, so what is 5? 5 is 101. What is 8? 8 is 1000. Yes, and if you do a OR here, what you are going to get? You are going to get 1 here, 1 here, 0 here, and 1 here. So what is this number? This is 8, this is 4, this is 2, and this is 1. So if you add 8 plus 4 plus 1, so this number is actually 13. Okay, so these are actually powers of 2. So 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, and 2 raised to the power 3. So you can see I am doing 8 plus 4 plus 1, that is 13. Okay, so this number is actually 13. So if you do this in your code, you will get an output of 13 in this particular case. So I hope binary OR is also clear. And now let us move on to XOR. So XOR is also known as exclusive OR. Okay, exclusive OR. So what are the rules of XOR? So it basically means if both the bits are same, then the result is going to be 0. For example, 0 XOR 0 is 0, and also 1 XOR 0 is 1 XOR 1 is also 0. So if both the bits are same, the result is 0. Otherwise, if both the bits are different, then the result is 1. So if I show you, maybe if I do 5 XOR 7, so 5 is what? 5 is 0000101, and 7 is 00111. Now if I do a XOR here, then 1 XOR 1 is going to be 0, 0 XOR 1 is going to be 1, this is going to be 0 and lots of zeros. So this result is going to be 2. Okay, so if you do something like cout 5s or 7, then it is going to print 2 in your code. Okay, so I hope you understood this XOR operator as well. So the next that we are going to discuss is NOT. Okay, so the NOT is a very simple operator. So what it does, if I have a bit 0, okay, let's say this is not the integer 0, this is the bit 0. So if you do a NOT of 0, you're going to get 1. And suppose you do NOT of some number, okay, let's say you have a number like 0 0 0 1 0 1. Let's say this number is 5. If you do the NOT of 5, then it is going to flip all the bits. Okay, so NOT of 1 is 0 and NOT of this is going to be lots of ones followed by 0 1 0 1. Okay, so this you will see it is going to flip all the bits including the most significant bit, that is the sign bit. Okay, that is the sign bit. So that means this number could be a negative number as well. Okay, now if you have little idea here, I can give you one example. Let's say I take something like this. Let's say I take int a and I say int a is 0 and I simply do cout not of a. Then what you're going to expect? Okay, what would be the answer? The answer is going to be actually not 1, but it would be -1. Okay, now you may wonder why it is so. So if you look 0 at the memory level, so what is 0? So 0 is a 32-bit number in which everything is 0. All the 32 bits are 0. So if you do a NOT of it, you will get all 32 bits as ones. Okay, and all 32 bits are ones, and the most significant bit represents the sign bit. Okay, so if this sign bit is 1, that means it is a negative number. So that means it is a negative number, and the remaining 31 bits, they represent the magnitude. Okay, now for the negative numbers, if we want to find out the magnitude of that particular number, so these numbers are stored in a form known as 2's complement form. Okay, they're stored in a 2's complement form. So in order to find out what number is this, what we need to do, we need to take the 2's complement, that means invert all the bits and add 1 to it. Okay, so the number is this. In order to find the magnitude, we have to first invert all the bits. If I invert all the bits, it becomes like this, and then I will add 1 to it. So this number is 0 0 0 0 0 1. So basically this is a negative number with a magnitude of 1, hence this number is actually -1. Okay, so if you do NOT of 0, and where 0 is an integer, you are going to get -1 as an output. Okay, and NOT of 0, where 0 is a bit, it would be 1. Okay, so that is something that you should be very careful while working on. Okay, so this something you can try it on your own as well. Okay, if you don't trust me, I am going to show you the demo as well. So I have this code where I have x is 0 and I'm doing cout not of x. So let us run this code and see what we get as an output. This should be /bitwise. So you can see this output is actually -1. That is because of the same reason I have discussed. Okay, so doing a negation of all zeros gives us a number in which all numbers are ones, and since it is stored as a 2's complement form, the first bit denotes the sign bit, the remaining bits denote the magnitude, and in order to find the exact magnitude we have to take 2's complement. So this process is known as 2's complement, where we invert all the bits and add 1 to it, and whatever you get, this number, this is the magnitude of the number. Okay, so if you convert this number into decimal, this number is 1, and sign is -1 because the most significant bit is 1. Okay, so I hope this is clear, and now you understand that doing a negation of a bit 0 is 1 and doing a negation of an integer 0 is -1. It's an important concept, so I have explained it to you. So binary NOT is clear. Now we will talk about two more operators, left shift and right shift, in the next lecture.